All right, so picking up with where we ended at the end of lecture. All right, I've got this set up right here, and I want to find I short circuit. And I'm going to again use the nodal analysis approach. All right, so this is just like the question you guys asked me from number 4. So what I'm going to do here is I'm going to say, all right, I'm going to call this here V1. I had to find a bunch of polarities. I call this I1. I think I called this I2. I called this I3, and I called this I4. All right. So in this case, I have, I'm going to do nodal analysis here. I'm trying to figure out what I short circuit is. Okay. So what's the unknown node here for me? Well, it's Vx. So, all right. So at the Vx node, what do I have? Help me out with writing that. How do I write the nodal equation here? What's the KCL in terms of the currents? I1, I2, and I3. Yeah, I1 goes in, and that's equal to I2 plus I3. Okay. All right, what's I1? Well, there's really 2 steps to writing this equation in terms of nodal, right? Well, the way I think about it is, here's V1 is the voltage across R1, right? So I have V1 divided by R1. This is V2. This is V3 right here. Okay. So the way I can do this is I write everything out now in terms of Ohm's law. So V1 is the voltage across R1. So I say V1 over R1 is I1. I2 is basically V2 divided by R2. And then I3 would be V3 divided by R3. So I'm doing that super slow. Those are not nodes here, right? So now I do this in terms of node voltages. All right. So what's the node voltage? So V1 is the voltage across R1 right there. So what do? I say the node voltage at the plus node minus the node voltage at the negative node. What's the node voltage at the positive node? What's the node voltage at the positive node for this guy? At the positive node, it's V, right? So the positive node there, the plus node on the resistor, is at that voltage source V, minus the node voltage at the negative terminal is Vx. So that divided by R1, that's then equal to V2 divided by R2. So V2, we say, the voltage at the plus terminal on that second resistor is Vx. The node voltage at the negative terminal is 0. So that divided by what I called R2. What about V3 up there? What's that? What's V3, the voltage across that capacitor? The node voltage at the plus terminal is what? Vx. What's the node voltage at the negative terminal? At the negative terminal is 0, right? Because this guy is shorted to ground right there. So that's definitely 0 volts. So I say this is plus Vx minus 0 divided by Z sub C. All right. Are you guys with me there? Now, this is one equation and one unknown. So I'd solve for Vx. So like I was saying, I think this is the way, I called it V1 here. All right, so let me write it like this. So for those of you that were not there in lecture, I made this statement about you guys worry too freaking much about simplifying your math. All right, way too freaking much about that. You don't have to. I don't care. This is not a math class. This is a circuits class. I want to see your circuits equations. What I like to do is I like to write this guy like this and use variables, and then I can write the variables in my MATLAB code and I can match the 2 of them together. Right? That makes it a lot easier for me to track where I made mistakes. You guys will do 38 steps of simplification in your math, and you will make a mistake, right? You may not make a mistake, but I would, right? I would assume that you would too, right? So I would try to keep it simple. Don't have to, but it's my recommendation. All right, so what I do here is I get the Vx terms all by themselves. So I write this as Vx. That's my unknown. So I have V over R1. V is the value of that voltage source. I know it. So what's the coefficient on the Vx here? How do I write that? 1 over R1. Yep, like that. Then basically what I'd say is Vx is equal to V over R1 times 1 over that whole ugly looking thing. And I wouldn't simplify it any further than that, right? Because any further simplification doesn't really help, right? So here's how I did. I guess in my code, I called it V1. This is actually Vx right here, all right? So what I did was I said V over R1. That's what I had here, right? So V over R1 times the inverse of that whole expression. So I have V over R1 times 1 over R1 plus 1 over R2 plus 1 over Z sub C to the -1 power, right? 1 over that. So I can clearly look at this equation and I can look at my equation that I wrote by hand and they should match, right? And I wouldn't simplify it any further than that. And I certainly wouldn't put numbers in there because when I put numbers in there, it just loses all meaning to me. It's really hard for me to do it, to do a gut check on whether it looks right. Okay. All right. Then once I do that, I get my value of V sub X. Okay. So that doesn't tell me what I wanted. What was I trying to figure out first place? We always forget that. What was I trying to find in the first place? Yeah, I short circuit. So how do I get I short circuit? Once I have Vx, I'll have that number once I solve this. All right, my code here will solve that. It'll give me a number. I don't think I wrote down what the number is. What do I do once I have that? All right. What do I do once I have that? To get I short circuit. So I short circuit is the current that's going into that short. So what would I do to get that? I do a KCL, right? I short circuit is equal to what by KCL in terms of the way I drew this here? So I short circuit's the current coming out of this node, right? So that's in terms of the currents I wrote there, that's equal to what? I4 plus I3. So it's I3 plus I4. How do I define I3? I3 is Vx minus 0 divided by Z sub C. What's I4? So I4 is the current in this resistor here. How would I define that? It's going this direction. 10 Vx, yep, because that's the voltage at that voltage source, right? Minus 0, because that's the voltage at that node, right? Divided by R3. At this point, I know what Vx is. So I basically plug it in and I get what I short circuit is. So it's just like the number 4, right? And so again, I did this in V1, but if I called that Vx, all right. If you look at this, this is 10 times Vx divided by R3 plus Vx divided by ZC. That's exactly what I have right here, right? So I like that because I can always look at my math and I can look at my MATLAB and they match each other. And then I always usually do this to see, okay, what's the magnitude and what's the angle of it, okay? All right, so at the end, I end up with, if I go through this process, I didn't write down what I short circuit was, but I did write down for myself what Z Thevenin was. All right, so this guy is ultimately VOC Z Thevenin, like that, okay? And my Z Thevenin is VOC divided by I short circuit. If I do the math for that, it works out to be 91.2 minus J 38.4. All right. Now the units on both the real and imaginary part are ohms, right? So magnitudes, these are always in ohms, right? So as a series combination of elements, what must that be? What components must I have there? What's the real part? Well, it's 91.2 ohms, that's right. So what physical part would that be? Be a resistor, right? That 91.2, right? So if I think about this, Z Thevenin would be a 91.2 ohm resistor in series with something with a negative, a capacitor. Yeah, this would be a capacitor here that had negative J 38.4. Okay. So I could think of that Z Thevenin as basically being those two things in series with each other. And I think you've got a question like that on the homework, right? This is negative J 38.4, and this is 91.2, like that. All right, now, let's say I ask you, like I think I do on the homework, what is the value of that capacitor? How would I do that? How would I figure out the value of the capacitor that's there? I know it's a 91.2 ohm resistor, and I know it's a capacitor whose impedance is 38.4 ohms. Well, so what's the impedance of a capacitor? 1 over J omega C. So if I let's just talk in terms of magnitudes to keep it simple, right? So I think the magnitude of those things. What's the magnitude of both sides? The magnitude of Z sub C is that. What's the magnitude of 1 over J omega C? 1 over omega C. Right? 1 over omega C. So 1 over omega C is apparently equal to 38.4. Right? We know what omega is in this case. All right, back at the very beginning of the problem, I said what it was. It was what? 300. All right, so I plug in here 1 over 300. Oops. 1 over 300 times C. And solve for C. I think my C in this case works out to be, if I go through the math, 86.8 microfarads. All right, and microfarads in general, that's a pretty big capacitor. All right, farads were, as a unit, were not chosen all that particularly well. All right, a 1 microfarad capacitor is a pretty big capacitor. All right, questions about that? If you want to see the beginning of that problem, go back to the lecture video later. Yeah. You got a question? Okay. All right. Okay, so I said there were 4 examples. If I don't get through them all, that's fine. All right, so this one I wanted to do because it's intimidating looking little butter. In terms of, you know, just seeing all the stuff going on here, dependent sources and all kinds of crazy stuff going on. How would I approach this particular one? I would take mesh with this guy. Would be my approach. So what would I do here? What would I do? If I do mesh, what's the first thing I do? It may not be the first thing you do, but it's the first thing I do. Pretend you're me. Write down the polarities. Yeah, write down the polarities for everything. So, all right, help me out. Which polarities would you choose? Let's go around. Let's start with the 4 ohm resistor. You want to do minus plus? All right, we're going to do minus plus. All right, Demetrius, you're next. What do you want to pick for the 2.5?
Let's keep it consistent.
Let's keep it consistent. All right, let's be consistent. All right. V delta they chose for us there. So we're going to go with that guy. And then what are we gonna do? We get to the 8 ohms. So I'm going around in a, what's that, clockwise. I always have to think about that. What do I do for the 8 ohms? Plus minus, all right. And then I got V theta. Sorry, I took this from a book. I wouldn't have probably done Greek. V theta. And then 6 ohms. What about it? Which way you want to go? Plus minus like this? Okay. All right. Now we got it. Okie doke. All right, it's gonna get ugly. I'm gonna call this V8. I'm gonna call this V6. Call this V4. I'll call this V2.5. All right. So I have a super mesh, do I not? All right. Got 2 super meshes, do I not? All right. So basically my super mesh, let's see, what are my 2 super mesh? What are the auxiliary equations we say for the super mesh? Would be what? I'm gonna write them off to the side. I'm gonna write them up here. So 0.5 amps equals what? IC plus IB, based on the way I drew these. IC plus IB. Okay? Because both IC and IB are going in the direction of that arrow. Okay? All right. How about for my other super mesh auxiliary relationship here? 0.4 V delta is equal to what? IA, yep, IA is going with it. IB is going against it. Now, what is V delta? Two multiplied by IC. Now notice that IC is going to the plus terminal of V delta, right? So I would say it's, yeah, 0.4 times 2 times IC is equal to IA minus IB. Now, without too much work, I've already got 2 equations and 2 unknowns. Well, 2 equations, 3 unknowns. I need a 3rd equation. All right. So I got a super mesh here. What's the super mesh I look at? Where do I write my KVL? None of the meshes with the current source, right? So where do I do this? Starting from the bottom left and go around the outside, right? Right, around the outside here. So let's see. So how would I do this? I'm slow. I'm going to do this in terms of the voltages, right? So I'm going to start in the bottom left corner, right? So negative 193. Then I'm going to go through V4, V2.5, V delta. I'm going to go around that way. So what do I write for V4? Negative V4, right? Negative V4. Because I'm going up from negative to positive. Then for V2.5, I'm going from negative to positive. So I say V2.5. What do I do for the 2 ohm resistor there, V delta? That's plus V delta. Because I go plus to minus. All right? You can make whatever definitions you want to, all right, as long as you stay consistent with whatever you do. All right, so what do I do when I get to the point that voltage source there? Plus 0.8 times V theta. All right, then I have V8, and I go V8 because I'm going plus to minus. Then what? Negative, yeah, and it's not a non, it's a theta, yeah. Yeah, it's awfully nerdy. Minus V theta, because I'm going minus the plus through that guy. And then what about V6 there? Plus V6. All right, so now I've got my KCL. All right, now what I'm going to do is I'm going to move the 193 over to the other side. So I'm going to say 193 is that. All right, so now what do I do with everything else in there? V4, V2.5, V delta. Well, now I got to start putting the mesh currents in there. All right, so how do I do it? So negative V4, let's just be clear about the setup. Negative V4, negative V2.5, plus V delta, plus 0.8 V theta, plus V8, minus V theta, plus V6. All right. Now, what I do at this point is I make all the substitutions I need to make. All right. So helpful for me, probably, what I would probably even do is outside of this is I would just write down, okay, what is V4 in terms of the resistors and the mesh currents? V4 is equal to what? It's 4 times IA. Yep. Okay. And I guess I was using capitals for those. All right. What about V2.5? What would that be? 2.5 IB. All right. And again, because the current's going into the plus terminal. Then what's V delta? 2IC. Okay. Then what's V8? (8IC). Okay. Then what about V theta? What's that one going to be? Where's the current coming in? Is it coming into the plus? It's going into the plus, right? Right, so it's coming into the plus. So it would be 7.5 times IB. Like that. And then what about V6? What is it? Yep, negative 6 IA. Why negative? Yep, IA is coming out of the plus terminal, right? So I'd take all those things and I'd plug them all into here, right? And then I have basically 3 equations and 3 unknowns, okay? So I'd plug all that stuff in together. You guys follow me where I got that? Right? Now, that would be one equation. I'm still left with this. I guess I already plugged it in here, right? So 0.4 times 2 IC equals IA minus IB. I put all that together and solve. All right. This is about as tricky a problem as I'm gonna see, right? And the important thing for me, the other thing I guess I'd have to worry about here is this guy, 0.8 V theta, right? I would have to worry about that. So 0.8 V theta, well, I've defined V theta here as 7.5 IB. So this would be 0.8 times 7.5 times IB. I'm going to have 1 equation, 2 equations, 3 equations, 3 unknowns. This is as ugly as you're going to find, right? But this is a situation where, again, hopefully to make clear, there's, a sign that comes from the KVL, right? As I write the voltages, there's a sign that comes from the passive sign convention. There's a sign that comes from, which direction the currents are going relative to the current in the resistor. And then potentially there's a sign from the impedance. In this case, it's resistors, so we're fine. But if I had an inductor's okay. If I had a capacitor, what's a capacitor? Well, it's got a negative impedance potentially. So it just makes everything really complicated for you. All right. So this is about as complicated as it gets, but this is a good example of how to deal with a mesh problem. All right. All right, one more. All right, let's deal with this guy here. Let's say I wanted to find the voltage VAB there. All right, so I got a 50 ohm resistor. Okay, how would you do that? I made meshes, so maybe that makes it look like you should do meshes. You do meshes. Who wants to do mesh analysis? All right, fair enough. We could do, so yeah, we could do that. I don't want to. How do I want to do it? Probably a way you don't want to do it, right? So yeah, I want to do it a way you don't want to do it. I want to take the 50 ohms out. And then I want to take the 50 ohms out and I want to convert this circuit here to basically 136. So I'm going to call it V here, where this is V. And I'm going to say, here's my inductor, here's my resistor, here's A. Call this R1, R2, A, B, ZL, and ZC. I'm going to do it that way. I took the 50 ohms out. Now, why did I do it that way? Yes. So in this problem, what I really want to find is I want to find VAB. So VAB for me is the voltage across that 50 ohm resistor. So what I'm doing is I'm saying take it out, all right? Make a Thevenin equivalent looking into these terminals. So there's going to be basically a VOC, some Z Thevenin, and then I'm going to put the 50 ohms back in. And this would be VAB. That's the approach I'm taking. Okay. So how do I do it? Well, so before we do the equivalent impedance, let's do the open circuit voltage first. All right. How do I do the open circuit voltage? What's that? Totally good. I don't want to though. If I was going to do that, I would have done mesh on the original circuit. Right. You can use KVL on the. You do KVL, you're doing you do KVL, you do KCL. You do KVL, you're doing mesh. If you do KCL, you're doing node. Nothing wrong with that, right? But I don't want to do either one of those. Yeah. It's just what? Well, let me ask you this. The voltage, so let's say, technically these are nodes right here. This is node. So this would be VA right here. This would be VB right here, wouldn't it? Can I say that VAB is equal to VA minus VB? Yeah. So I just got to find VA and VB, don't I? So what is VA and VB? I got voltage divider. I got two voltage dividers. Yeah. Where are they? Yeah, basically I know the voltage across each of those guys. So I have the L and the R1 in series, and then I have the capacitor and the R2 in series. All right. So what would I do for VA? I'd say VA is what? It's V. And again, if you don't remember the voltage divider relationship, what do I say? It's the current times whatever impedance I'm looking for. All right. So for the VA path, what's the current through this path right here? What's that current? Okay, we can call it IA, right? And so how would I define it in terms of the circuit here? V divided by ZL plus R1. That's the current in that path. So that current times R1 would be that voltage. All right. VB, what would that be? How would I define that guy? V over what? ZC plus R2 times what? R2. Let's say I wanted to find the voltage across the capacitor instead. What would that be? Instead of R2 would be ZC. Yeah, that's right. It'd be the same current. This term would be the same, but I'd multiply by ZC right there. Okay. So VA minus VB is that. All right. So that is basically my VOC right here. Okay. How do I get Z Thevenin? All right. So my circuit was like this. Here's V. Here's ZL. Here's R1. Here's Z sub C. All right. How do I figure out my Z Thevenin here? I don't need to do the short circuit in this case. I could if I wanted to, but I don't have to. How do I do it? Turn off the voltage source, which means make it a short, right? Okay. All right. So what's going on here? So so we're talking about basically if I had a current source that was connected here, what would be the current what would be the impedance that it flows through? What would be the impedance that it flows through? How do I approach this?
Can we say ZL the series with R1 and then therefore load the parallel with
well, okay, so clearly ZL and R1, it's a little hard to say that they're in series because if I look at this, there's going to be a current here and a current here, and they're going to recombine there, right? So I know that they're going to be different. Now, what else can I say? Say that again? ZL plus ZC in parallel with R1 plus R2. Let's see. So a current that goes in here would split here and here. And then where would it go? We go through the short circuit. Well, that wouldn't give me a complete loop to flow through, right? So
the current going through ZC would go back to ZL.
Yeah. So just let's you're right. If I think about the path here, current would go here, current would go here. Current has to flow in a complete loop. So if I took a current flowing this way, going this way here, right? How does it get back? How is that? So it couldn't. Why not? Why wouldn't it go through ZL? Well, when I look at this here, this is tricky with that short right there. I can see that looking at this, what do I know about the voltage across R1 and the voltage across ZL?
The same.
It'd be the same depending on how I drew the polarities, it'd be the same voltage, right? How can I tell that? If I do a KVL around this loop right here, right? If I do a KVL around this loop right there, what I see is that the voltage across the inductor and the voltage across the resistor is the same. Depending on the polarity, they're either they're the same magnitude, maybe the opposite sign, depending on how I do the polarity, right? So when I look at what's actually happening here, right, what I actually have is it would appear the same is true for the capacitor and the resistor. So it looks like to me, I have ZC and R2 in parallel, right? ZC and R2 are in parallel because the total current entering these two guys, they've got the same voltage across them, right? I have the same voltage across those, they're in parallel. Right? That current that enters a parallel combination all comes out on the other side. So basically what I end up having here is Z sub C in parallel with R2. That is in series with Z sub L in parallel with R1. That's the combination that I have. Right? Now, let's say you were like, oh, I have no idea what you just did. Right? If you didn't know, well, what I could do is I could basically figure out for myself, I could call this I test if I wanted to. And I could say, all right, well, figure out what the voltage is right here. Because what's true about that? If I figure out that voltage, V divided by I test is equal to some R value, right? Or some Z value, I should say specifically, right? So if you really weren't sure, that would be the way to do it. Basically say, figure out what that V is in terms of I test, and what you would get would basically be this result. All right, this is a pretty tricky one, right? Because that short definitely messes everybody up. But this is why I wanted to do it this way rather than mesh, again, to get you thinking. Yeah.
ZC and inductor or is it just because of that short there?
So yeah, that's a good question, right? So when I look at this here, again, I'm looking at it from the perspective of a current that flows into the terminals. ZC and ZL are not in parallel because if I go around the loop that contains them, there is also this terminal here. So the loop would include this, and this. So they're not in parallel with each other. Whereas if I go around this loop here, I can see ZL and R1 have the same voltage across them. If I go around the outer loop, I see that ZC and R2 have the same voltage across them. That's a tricky problem. All right. So, and the way that I kind of think about this basically is the current that enters this parallel combination then enters this parallel combination and flows back out. That's the way I think about it. Again, the way you could really do this, and I could do this slowly, would be to say, if I applied a current here, I could figure out what voltage it creates. And then that voltage divided by that current is equal to whatever that equivalent impedance is. That's the fancy way of doing it. But you would see that it would work out to be this picture that I drew right here. All right.